Our next presenter is Brian Reese. He's going to be talking about remote sensing, monitoring HABs with satellite data. Brian holds a master's in natural resource management from the University of Idaho. He is currently a Water Quality Standards Analyst and lead Harmful Algal Bloom Coordinator at the Idaho Department of Environmental Quality. He is a valuable resource for answers to questions regarding cyanobacteria. Brian, you've got your presentation on and you're going to be joining us verbally, I believe.
Good morning. Yeah, thanks, Gary. It must be DEQ Employee Day for poor connectivity. I was asked to give a walkthrough of the new DEQ Harmful Algal Bloom website, and HAB or HAB stands for Harmful Algal Bloom. And we have a new map resource hosted in a linked story map. We recognized a need to share the satellite data we use with the public, and I thought it best to present the technology behind the new map and give a very simplified explanation for how it works. The DEQ HAB monitoring program is a response-based program, meaning that we respond to reports of potential blooms rather than proactively monitoring. This is primarily due to the fact that we don't hire a seasonal HAB monitoring crew like we do for some of our other seasonal field work, and HAB monitoring falls on top of our surface water program staff, and it is added on top of their position responsibilities. Remotely monitoring cyanobacteria harmful algal blooms has relieved some of the workload by allowing DEQ staff to watch the progression of a bloom once it has been confirmed and see when it begins to decline. Most of our offices have one or two people who respond to reported blooms to collect the samples and monitor throughout the season. Many of the water bodies we monitor are several hours from their offices, and it takes a significant amount of time to get out and back. We have been using and testing this tool for a couple of years, and we wanted to be able to share the data with people who use our lakes and reservoirs. First off, we monitor cyanotoxins because they are potent chemical compounds that happen to be toxic to many animals and people. The data indicate that blooms are occurring more frequently and they are becoming more toxic. Ingesting cyanobacteria and cyanotoxins can have real consequences. And every year I talk with people who lose dogs and horses, but the worst are the calls and emails from parents who want to know if playing in lake water could have made their child very sick. The data we primarily use comes from the European Space Agency's Sentinel satellite program. NASA, USGS, and the EPA collaborated to develop a program called the Cyanobacteria Assessment Network, or CYAN, that they analyzed the data from the ESA Sentinel-2A and Sentinel-2B satellites. The CYAN program processes the data and makes it available to the public and agencies like DEQ. The ESA data is available through their website, the Sentinel Hub Playground, and the CYAN data is available through the CYAN app in Google Play. Sorry, iPhone users. And now the DEQ website and a handful of other states' websites. Most, if not all of us, frequently use satellite images through the mapping apps and websites on our phones and in our cars. The data we use to monitor cyanobacteria blooms is collected in a very similar manner, but contains more data. Like the images we use with our GPS apps, the satellite data used to remotely sense blooms is from the visible spectrum. Unlike the imagery in Google Maps, this data is collected from discrete bands of the light that is reflected back into space from the landscape. Most of the data we use is from the Sentinel-2 and Sentinel-3 satellite projects. There are two types of resolutions we are concerned with. Spatial resolution, which is defined by the number of pixels in an image, just like in the digital cameras we all use, and spectral resolution, meaning the tool can define fine wavelength intervals of light. This lets us study the things on the landscape that reflect light back into space. Sentinel-2 has a much higher spatial resolution with a 10 meter by 10 meter pixel versus the Sentinel-3 300 meter by 300. This means the product from each Sentinel platform has inherent limitations and that they make complementary tools. And I'll discuss this in a couple of slides. When we look at the remote sensing data, we see images, like the satellite imagery in the mapping apps. However, these images are different because they rely on a combination of the different spectral bands collected by the sensors. We can pick and choose which bands of data we use and gain insight about the landscape in the image. For instance, the pigments that allow plants and algae to photosynthesize use and reflect specific wavelengths of light. Knowing what pigments cyanobacteria reflect allows us to look for them in the data. Currently, the data we use is based on the pigments in microcystis. Like I mentioned earlier, if you want to use the Sentinel-2 data yourself, it's available at the Sentinel Hub Playground, and I use it all the time. This data is available year-round, and it can be used to see all kinds of information about the landscape, including snow coverage. To start using this tool, enter the location at the search box at the top right. I mention this because it's sometimes hard to find. The data shown is always from the most recent overflight. By clicking on the calendar, we can select a different date and see when the overflights occurred and when usable data was collected. The circles show when the satellites passed over this area. Light gray indicates that data was collected. Dark gray indicates that data was not collected, which usually means clouds or wildfire smoke obscured the area. There is a setting in the Effects tab, which is here, on the left for showing the date of the overflight. Next, we can use the rendering tool and select the bands we want through the custom menu. And for the sake of time, I'm going to move through this section fairly quickly. My email address is on the final slide if you'd like to contact me, and I'm happy to talk and answer questions. Using the information in this paper by Xi et al., I was able to find the target wavelengths needed to help see the cyanobacteria in our lakes. The ESA provides the spectrum we can select from. I most commonly use 1, 3, and 4, but you'll notice that in this image I used 1, 3, and 12, and filter 11 can be used as well. Regardless, the very dark or black areas in the water body indicate a low probability of a cyanobacteria bloom. Even though it can be faint, green indicates the possibility of a bloom. The cyano peaks and filters are not a perfect match, but they are close enough for our purposes. And a quick side note, last week while I was editing this presentation, I saw that there is now a preset filter based on bands 1, 3, and 4, and I would just use that. You may have seen these images from CyanoTracker. They were created using Sentinel-2 data. I suspect they emphasized the swirly green colors with photo editing software. And after first seeing these images from CyanoTracker, I started using software to enhance the colors too. And it makes the faint colors easier to see. This image illustrates the inherent spatial resolution difference between two Sentinel platforms. Because we're trying to sense the pigments in photosynthesis, we have to be aware that shoreline vegetation and aquatic plants are also picked up and can be misread by Sentinel-3 as a potential bloom. For this reason, and given the large size of the pixels, cyan works best with large waters. Looking at this image, only the dark pixels near the center of the canyon give reliable data. It would, however, be a mistake to think that we should use the sharper, clear Sentinel-2 data only, because the spectral resolution of Sentinel-3 is much better than the spectral data we get from Sentinel-2. We can use the Sentinel-3 data to estimate the population density of a cyanobacteria bloom in a lake or reservoir. And shoreline data can be useful when compared with the Sentinel-2 data, which, with its higher spatial resolution, allows us to see if the water closer to the shoreline is also green. So using the two tools with data from last September, I can clearly see in this image that there are areas with a potential bloom. However, with the Sentinel-3 data, it indicates a widespread bloom and provides an estimate of the density of the cyanobacteria population in a given pixel. Now we finally get to the website walkthrough I was asked to give today. Under the Water tab in the new DEQ website is a link to the new HAB page. The HAB page will still have the health advisory map, and it will show the active and lifted health advisories. There are 2 links to the story map and the new potential bloom map. There, below the image on the header, there are links to the health advisory map and the potential bloom map, and you can scroll down as well. The potential bloom map is actually 2 maps superimposed on one another. The slider in the middle can be moved to cover or reveal one map or the other. The arrows in the top right corner of the map expand to full screen. This is Pend Oreille Lake in North Idaho. Last week, and yes, it looks like a bloom may be occurring. The map imagery on the left is normal with satellite imagery, and the colored pixels within the lake show the new cyan data. It is important to note that ice can be misread as a bloom, although the cyan algorithms normally indicate no data with ice. To see whether or not the lake is frozen, I use the Sentinel Hub playground to see what the lake looks like. And it's not frozen. It looks like Pend Oreille may be experiencing a bloom. During the summer, I would let our staff know and they would investigate. During the winter, we're not concerned with recreation exposure and we won't collect a sample. I would like to know what's there, but budget and staffing constraints limit our ability to respond to every potential bloom, especially during winter. Looking at the cyan color index scale, it looks like we have a range of population densities from low thousands to around 100,000 cells per milliliter in areas along the western shore. The green, yellow, and red boxes, diamonds and circles in the key, show the population density threshold set by DEQ, the Department of Health and Welfare, and the health districts. And these are intended to keep people safe, and these thresholds are based on human health studies and Idaho data. Moving the slider to the left shows the current data with the diamond symbols, and the old data are indicated with circles. Now this is a jumble, so if we zoom in on the lake, we can see the individual pixels and the data they contain. Clicking on one of the pixels opens up a pop-up box with information and the data was collected. So for instance, in this date, it was estimated this pixel had about 143,000 cells per milliliter. You can scroll through the other dates with the arrows on the bottom right corner and see what other data was there. So with that, I see I'm just over time and I'm going to skip to the end and conclude my presentation, and I will take questions.
Excellent. Thank you, Brian. Right now, it looks like our Q&A is still wide open. So if you don't mind keeping an eye on that, and we'll be in touch if someone has a question for you. Otherwise, I'm just going to keep on going to our next panelist. Again, thank you for your presentation.